All right, so we're gonna spend some time on vectors. Oops. Vectors in R2 and R3. So you know what R2 is. It's usually depicted by the XY plane. And a vector right here is the origin. A vector is usually depicted by a pair of points, a pair of numbers like that. In R3, you have 3 directions, X, Y, and Z. And a vector, again, you have an origin. A vector is then depicted by 3 numbers. Now, suppose you have 2 vectors in R2, like U and V. Then we can do the following thing. And one of the operations we do to vectors is what's called vector addition. U plus V, that allows us to form U plus V, which is in simple term given by just adding the components. Similarly, if you have vectors in R3, you can do that too. Suppose you have U and V now are vectors in R3, then U plus V is again defined simply by adding the components. Okay, and geometrically, you have 2 vectors, say U here and V there. Oops. Now, to form U plus V, the thing you do is you draw a parallelogram with U and V as 2 sides, like that. This is a parallelogram. And then this vector, the diagonal vector, this is U plus V. Okay. So that's one operation we do to vectors. Another one is called scalar multiplication. Okay, and now for this you need a scalar, say C. Scalar. Then we can define C times U simply by multiplying the entries. In R2 it's just this. In R3 it's it's 3 entries rather than 2. Okay. And again, you can interpret this geometrically. If you have a vector U, now CU will scale the vector according to C. Now, if C is positive, CU and U would point towards the same direction. If C is negative, the direction would be opposite. Okay. Now, one thing we've also did before is the dot product. For two vectors, we've introduced the dot product. U dot V is a scalar formed by multiplying the corresponding entries together and add them. So in R2, you just have U1 V1 plus U2 V2. For R3, you have U1 V1 plus U2 V2 plus U3 V3. Okay. Okay. Now, geometrically, the interpretation of U dot V is this. Again, let's say you have U and V, like that. And if you put two vectors like these with the same origin, then they form an angle called theta. Then U dot V is equal to U V cosine theta. Okay. That's the here U and V are lenses of V, lenses of these vectors. So U is the U dot U square root. V is V dot V square root. Okay. So in other words, geometrically, dot product gives you a way to measure the angle formed by the two vectors. Okay. So now there's one operation that's special in R3. That's called cross product. Okay, so let's say you have two vectors, U, U1, U2, U3, and V, V1, V2, V3. Then their cross product is defined by the following expression. First of all, the notation is U times V, or U cross V. And it's a three-dimensional vector. The entries are U2V3 minus U3V2, U3V1 minus U1V3, U1U2 minus U1U2, that makes no sense. U1V2 minus U2V1. Okay, so this is the cross product. It's just, at this point, it's just a definition. Now, it has some properties. Okay, so the easy ones are the following. If you form U cross U, you get a zero vector. If you form U cross 0, you get a zero vector. If you form U cross V or V cross U, they are not equal. They differ by a sign. Okay. Now, if you form, now if you have three vectors, say u, v, and w, you can consider u cross v plus w, and this is equal to u cross v plus u cross w. Okay. 5. Likewise, if you have u plus v cross w, this is u cross w plus v cross w. Next property, if you have a scalar c, and c times u is a vector, you can then consider it cross v. That's the same as c times u cross v. Also the same as u times cv, u cross cv. Okay. Yes. Now, okay, so these are the easy properties. Oh, there's yeah. Then there's a geometric interpretation as follows. So now you have, again, you have two vectors, say u and v. Okay. Now u cross v is determined as follows. It's going to be a vector, obviously. That's first of all going to go, u cross v is going to be perpendicular. Oops, not that. U cross v is perpendicular to both u and v, and there are two directions that are perpendicular to both u and v, and they are opposite directions. And the way to decide which direction u cross v is by the so-called right-hand rule. That is, if you start from u, sweep to your four fingers of your right hand from u to v, then the direction your thumb points toward is the direction of u cross v. Okay. All right. Now again, if you put the vectors u and v this way, there's an angle theta, then there's still a property, of cross product related, well, there's the following property of cross product. If you consider the size or the length of u cross v, it's equal to the length of u times the length of v times sine theta. Okay. Again, theta being the angle formed by u and v. Okay. So these are the main thing that we do to vectors in R2 and R3. And now we're gonna move on to Rn as a vector space. Now n is just arbitrary. Okay. Now recall, Now Rn is by definition the set of n tuples of real numbers. Okay. Now, besides being a set, we can actually do two operations. For elements in Rn. So let's see. So the first one, in fact, we've seen these operations already in R2 and R3. The first one is vector addition, which is defined in the same way as did for vectors in R2 and R3. Suppose you have, in this generality, two n-dimensional vectors x and y, then x plus y is defined to be the n-dimensional vector formed by adding the corresponding entries of x and y. Okay, so this still belongs to Rn. So that's the first operation we can do, vector addition. Now the second operation we can do is, again, just like the one we did in vectors in R2 and R3. It's called scalar multiplication. And for this, you need a scalar, say A, then A times x is defined to be ax1, ax2, axn. Namely, you multiply A to the entries of x one after another. The result is still a vector, n-dimensional vector. So, and that's called, this operation is called the scalar multiplication. Okay. Properties of these operations. I mean, there are quite a few properties of these operations, so we're just gonna take some time and list them all. Okay. So so suppose x, y, and z are all vectors in Rn, and a and b are scalars. Okay. Then the following holds. Okay. Now let's see. There's three. We put these properties into three categories. First one is closure property. C1. So x and y are vectors in Rn. So, and the first property is by definition of x plus y obviously belongs to Rn as well. Also, by definition of scalar multiplication, a times x is also in Rn as well. Now, the next class of properties are about additions. And they are as follows. A1 x plus y and y plus x are the same thing. And this is easy to see just by the definition because both vectors are formed by adding components of x's and y's respectively. So they are obviously equal. Now A2, if you have three vectors, you have two ways of adding them. You can choose the two to add first and then add the result, add the third to the result. Like these, you get y plus z plus x or x plus y plus z, and the property that you can check easily by comparing the components is that x plus y plus z is equal to x plus y plus z. Now, next property is that Rn contains a special vector called the zero vector. We've seen it before. It's the vector that has all the entries 0. And this zero vector has the nice property that for any x, x plus 0 is x. Right? And this is easily seen from the definition of x plus the vector addition, because zero vector has all its entries being 0. Adding 0 to a number will not change that number. Therefore, adding zero vector to x will not change x. Now, the next property is the following. For each x in Rn, there exists a vector, another vector, denoted by minus x in Rn, such that x plus minus x is the zero vector. Okay, and this is easy to construct. I mean, once you have x, if you can consider the vector whose entries are all the negatives of the entries of x, then that vector will play the role of negative x. Okay. Now, the next collection of properties concerns scalar multiplication. Okay. And here we have, let's see. And let's see, the first one is the following. Say you have two numbers, a and b, as we did in the beginning. Then you can consider b times x. That's a vector. You can consider a times b times x. And the claim or the property is that this is ab times x. And this is easily checked from the definition of scalar multiplication, because on either side, you're basically multiplying a and b to each component of the vector x. And for numbers, this property just holds. Okay, M2. The next property is, say you have x and y, two vectors, then you can form x plus y. And if you have another scalar a, you can consider a times x plus y. And this is a times x plus a times y. Again, this you just check check component-wise. And 3. Now suppose you have two numbers, a and b. You can form a plus b and times x. That's the same as a times x plus b times x. Again, check component-wise. Finally, the number 1 here plays a special role. That is, if you take 1 times x, you get back to x. Okay. All right. So now we have these many, like 10 properties. See, 2 closure properties. Now I have 2 closure properties, C1, C2, 4 properties of additions, A1 through A4, and 4 properties of multiplications, M1 through M4. Very well. Now, I mean, this all seems fairly easy. Now, what we're interested in here is not really about Rn itself, but rather subsets of Rn that have special properties. Okay, so a subset W of Rn is called a subspace. Vector subspace, maybe. If all properties above, namely C1 through C2, A1 through A4, and M1 through M4 hold. If all these 10 properties hold with W replacing N. That is, for vectors in W, we require the following thing. Two vectors in W, x and y, we must have x plus y also in W. Let's, in fact, write this more carefully. The properties that we need to hold are the following. Right? Suppose you have two vectors in, three vectors x and y and z in W, in this subset W, and a and b are still scalars, then we require that C1 to hold. Now that is x plus y also in W, and C2, that is ax, is also in W. A1, A2 are just equalities of two vectors, and they are supposed to hold. And A3 requires that W here contains the zero vector with O, so that x plus 0 is x for all x in W. A4 requires that for every x in W, there exists another vector, negative x, also in W, such that x plus minus negative x is 0. Now for M1, M2, and M3, they're just supposed to hold because they don't actually care whether these vectors are in W or in X or in Rn. M4 does. M4 requires that 1 times X is equal to X for all X in W. Okay. Now that is, again, a subset of the W of Rn is called a subspace, vector subspace, if all these properties above hold with Rn replaced by W. Okay. So let's see an example. Let's say W consists of all vectors of the form x1, x2, 0 in R3, with x1, x2, of course, being real. Now, by construction, W is a subset of R3. And in fact, we can draw a picture of it, right? If this is x1, x2, x3, x3 respectively, then x1, x2 is here. This is W, while the ambient space is R3. Okay, and it is easy but tedious, but lengthy, let's say, to check that all conditions of all properties above hold for W. Okay, so W is a subspace of R3. I mean, in fact, we know what this space is. W is R2. Right? The way it's defined, W just consists of pairs of numbers. It's a triple as written, but the third entry is always 0. So it's in fact a pair of numbers. That's R2. Okay. Now, like I said, we're going to be interested in subspaces. Going to be interested in subspaces. So, as you can see in the definition, subspaces are defined by the validity of 10 conditions, and it's going to be not so fun to check these 10 conditions every time we see a set and we would like to know if it's a subspace or not. So it would therefore be nice if there's a simpler way to check whether a subset is a subspace, and that's what this theorem next is about. So W, let's say, have a subset of Rn. Is a subspace if and only if the following conditions are met, or the following holds. So there are, instead of 10 conditions in the theorem, there are just 3. First one is the 0 vector is in W. Now, the second condition is if x and y are in W, then x plus y is in W. This is just C1, the first closure property. Now, S3 is if x is in W and C call it A, then A is in R, namely a scalar, then A times x is in W. This is just the closure property C2. Okay. Now, well, that's it. That's what the theorem says. If you just check these three properties, the two closure properties plus this statement that the zero vector is inside the subset W, then W is a subspace. Okay, now to prove this, well, we just have to check all the properties. As required, C1 and C2 are satisfied, right? Because they are S2 and S3 respectively. Now, M1, M2 just, sorry, not M1, M2, A1, A2 just hold because A1, A2 are true because X, Y, Z are vectors in Rn. Sorry, are vectors in W, which are vectors in Rn. Right, X, Y, Z are chosen to be vectors in W, so they are in fact in particular vectors in Rn. And as vectors in Rn, they have these properties. It doesn't matter where the properties take place, they just have to hold. Now A3 holds because of S1. Right, S1 requires that zero vectors in W is in W, which is what A3 needs. Right, A3 needs that. And these properties, x plus 0 is equal to x, that just holds true for any vectors in Rn. It just so happens that we only, for this purpose, we only look at vectors in W. Now A4, for A4, let's say you have x being a vector in W, then by S3 minus 1 times x is in W, right? And if you take x plus minus 1 times x, x being a vector in Rn, x is equal to 1 times x. And this is M, that's what we call M4 for x in Rn. Okay. Now we have two vectors, we have just one vector x, but multiplied by two different numbers, 1 and minus 1. Where is it? By M3. Again, for vector x in Rn, this is 1 plus minus 1 times x, which is 0 times x. And if you just check, 0 times x is 0. So this shows you that A4 holds true. Okay, now M1, M2, M3 just hold because they are vectors in W. M1, M2, M3. In fact, all four multiplicative properties just hold because the vectors are vectors in W, which hence are vectors in Rn. And they are, vectors in Rn have these properties. Okay. So now let's check some examples just to see how this theorem can be applied. Again, to apply this theorem, all you have to do, once you have a subset W, you just have to check these three properties or these three requirements. Okay. And now let's see. Let's pick some examples. One, say W is I don't know, x1, x2, x3, x1, x2, x3 all in R. And let's say x1 is equal to x2 plus x3. It's a set of triples, so it's definitely a subset of R3. Okay. Now, the question is this a subspace? And we're going to use the theorem to answer this question. To do that, we should begin with checking whether the zero vector is in W. And remember what the zero vector is. It's the vector whose entries are all 0. Right? And this is in W. In fact, at this point, you should actually have some idea about what being in W means. In fact, being in W means this. You're looking at being in W means that there's 3 entries in this triple have this property that the first one, x1, is the sum of the other 2. And now it's easy to see that for the zero vector, 0 is the sum of the other 2, which are both 0. So 0 is in W. Now, if I have 2 such triples, x1, x2, and x3, y1, y2, and y3. Again, being in W, being in W means that x1 is x2 plus x3, y1 is y2 plus y3. Now trying to add them. As by definition, the sum is the vector with entries x1 plus y1, x2 plus y2, and x3 plus y3. Now, again, I claim that this is going to be in W. And for this, you need to check whether the first entry, in this case x1 plus y1, is equal to the sum of the other two entries. And that's just true because the right hand side here is equal to x2 plus x3 plus y2 plus y3. And you could equate x1 with x2 plus x3 and y1 with y2 plus y3, and that will make this equation hold true. Hence, the resulting vector is in W. Now, the last property is about scalar multiplication. So you have, again, one vector in W. Again, this means x1 is equal to x2 plus x3. And say you have A, that's a real number. Then A times x1, x2, x3 is equal to the entry-wise multiplication, ax1, ax2, ax3. Now this is also in W because ax1 being the first entry here is equal to ax2 plus ax3. It's evident just by looking at this equation, x1 equals to x2 plus x3 and multiply both sides by a. Okay. So let's see. That's the three. These are the three conditions we need to check according to the theorem, and we check them all. So yes, this W is a subspace. Now, let's see here. Now let's look at some examples, or some other examples. So W, again, it's a subset of R3 consisting of triples like that. And what is, what is the special thing about this triple is that its last entry is always 1. Again, the question is this a subspace? And answer is no, because the zero vector that you need is not W. And the reason for that is easy, because the zero vector has all its entries 0. The last entry is in particular 0, not 1. Okay, so this W is therefore just a subset, not a subspace. Oops. Now, let's consider the following subset. Now let's do R2 instead. And we can do R3, no problem. So we consider W being the set of triples with the requirement that the entries are all integers. These are certainly, this certainly form a subset of R3. And the question is, are they, is this W a subspace? The answer is no. The answer is no in some Well, not the easiest possible way, because this W does contain the zero vector. Well, 0 is the vector with all entries 0, and 0 is an integer. So that satisfies the requirement of being in W. Right? Now, if you have two vectors, x and y, in W, then that means that the x's and the y's are all integers, right? Then you look at x plus y, that will be the vector with three entries, x1 plus y1, x2 plus y2, x3 plus y3. So, and these entries x1, because the x's and the y's are all integers, x1 plus y1 is an integer, and likewise for the others. So x plus y is in W. Well, but I'm telling you that W is not a subspace, so something must go wrong with the remaining property S2. That is, if you take A to be a real number and x to be a vector in W, then AX, the claim is that AX need not be in W. For example, let's take A to be a half and X to be the, one of the very easy vectors, 1, 1, 1. Then A times X is the vector with entries all being equal to 1/2. Because 1/2 is not an integer, this is not a vector in W. So S2 fails. Therefore, according to the theorem, this W is not a subspace. Okay. Now, let's just look at one more example. W is now this time just a subset of R2. Okay. Now the requirement for being in W is that one of the entries is 0. And the question is this a subspace? The answer is again no. And the reason is the following. You can again check that S1 holds, right? Because 0, 0 will certainly have one of the entries 0. You can also check that S3 holds. Because if you multiply your vector by a number, the entry that is 0 remains 0. Now S2 does not hold. That is because, for example, in order to show that S2 does not hold, I just need to give you two vectors so that the sum is not in W, right? So let's take 1, 0 and 0, 1. They're both vectors in W because both of them have one entry 0. But if you add them, you get a vector 1, 1, which is not in W because both entries are non-zero. Okay, so this shows that S2 fails. Therefore, by the theorem, W is not a vector subspace. Okay, so that's this lecture. We're gonna spend more time on vector subspaces in the next lecture.